Okay, today I thought I would do something very different because I realized the last time that I was saying lots of things about tensors and vectors and so on, but I didn't know how much of you remembered what tensors, vectors are and what they did and what they used. So I thought maybe I should just spend a little bit of time revising that part of it, just so that we are comfortable with what it means, and because what I want to do after this also has a bit of tensors and so on, a stress tensor, which is the Navier-Stokes equation, which describes a liquid, and I wanted to make sure that there was nobody who wasn't comfortable enough with that material yet. So let's just talk about simple things today, which is scalars, vectors, tensors, etc. What they mean. Okay? So as always, whenever we want to describe something, we have to say what it is that we want to describe, and typically that starts off by saying, here is my coordinate system. Here is some point P, and there are some properties associated with that point. Maybe there's some density at location R at time t, or some velocity at location R at time t, or maybe it's even a piece of surface here. And I have a vector from here that marks where that surface is. It's usually the first thing that we have to do. So let's start off by thinking of what is a scalar quantity. And for simplicity, maybe we'll just use a simple two-dimensional coordinate system with x here and y here. So if I have a point P here and some measurable quantity associated with that particular point, let's say that quantity is a temperature. So there's some temperature T as a function of that point x and y. Okay? The temperature is a scalar quantity, and it's scalar for the following reason. Let me imagine that I am describing this physical situation not in this coordinate system but another coordinate system. So another coordinate system I could use would be, for example, one that is simply rotated with respect to this earlier coordinate system by some angle theta. It's a perfectly reasonable way. A priori, there is nothing that tells me that in the universe there are fixed directions defining x, y, and z. I should be able to choose a coordinate system, whichever coordinate system I like, and the answers that I want to look for should be invariant with respect to the choice of that coordinate system. Okay? So now the point xy, which initially had coordinates here and here, has a different set of coordinates in the new system. So this point P might have a coordinate, say, x here and y here in the initial coordinate system, but it would have some coordinates, say, x prime, and let's see, where did I draw that? Y prime in the new rotated coordinate system. Okay, so with every point x comma y, I can associate another point x prime comma y prime. Okay. The statement that something is a scalar says that under this change of coordinates, this transformation of coordinates, the t at x and y becomes the t at the point x prime, y prime. That because it's a scalar, it is only magnitude. There is no direction with this quantity involved. Therefore, provided I'm looking at the same point, the number that I associated with that point should be the same, irrespective of whatever coordinate system I wind up using. Okay? So these are scalar quantities. They have a magnitude. So they have a value. So this is, for example, is a scalar field, the temperature, because the temperature is defined at every point in space. Here, let's in this example here, it's a field of scalar quantities. At every point I can tell you what the temperature is. If I change my coordinate system, the way I label that point changes, but the number that I associate with that point doesn't change. That's what I mean by a scalar quantity. And scalars, vectors, and tensors are always defined with respect to a definition like this. How do they behave when you change a coordinate system? Let's look at a different type of quantity, and that's a quantity that has a magnitude and a direction. These quantities are called vectors. And one example might be here, take your coordinate system here, think of a point here, there might be, let's imagine this point is the origin here, and from this point draw an arrow like this. Okay, so this has two quantities associated with it. One is the size of this arrow, which is the magnitude, and the other is the direction in which the arrow points. I can have the same magnitude of the arrow, but it could point in different directions. So now in this coordinate system, if I wanted to describe this, I would say there is a quantity, say Vx and Vy, that determines this direction in which it points. There is no longer a single number, but a pair of numbers in 2 dimensions, or a triplet of numbers in 3 dimensions, that specifies a direction from the origin pointing in this direction with a component of x and a component of y. The vector from the origin to this point here is also a similar quantity like that. It has an x coordinate and a y coordinate, but in general I can have some quantity associated with a point that has magnitude and a direction. So that's what specifies vectors, that you can think about them physically as having a magnitude and a direction. In 2 dimensions, you would parameterize them by 2 components, x and y, and this would be Vx times a little vector pointing in this direction, the x hat, plus Vy times y hat, and this would be the definition of a vector quantity V in terms of its components Vx and Vy. That is to say, I can think of this vector as being made up of one vector in this direction and one vector in this direction. So vectors add. If I have 2 vectors V1 and V2, V1 plus V2 is obtained by taking V2, adding that to the head of V1 and looking at where that final point lies with respect to the origin of the coordinate system. Just as in temperature, at every point in space, I could have a magnitude and a direction. And so I could have a vector field in general. And let's look at examples of vector fields. Suppose I had a charge sitting here. Suppose the charge was, say, plus q. And I wanted to ask, what is the force that another small charge, say, plus q prime, feels when it is here at some point r from this charge? Now, obviously, that quantity has a direction because it feels a force that is directed away, because these charges will repel each other if they have the same sign. So this is plus q and this is plus q prime. But the amount of that, the magnitude of that repulsion depends of course on how big q and q prime are and how large is the distance that separates the points, say p and p prime. Okay? So here is a quantity that has magnitude, which is how big the electric field is, that pushes from one to the other, how big the force is, as well as a direction which says where is it pushing. So that's one example, and I could put my test charge here or here or here or here or here or here or here. With every one of these points I would associate a magnitude and I would associate a direction. And that's what I mean by a vector. Okay. Now given vectors, we can do interesting things with them. First of all, the question to ask is, we said that if I took points x, y, which became x prime, y prime, my quantity t of x, y remains the quantity t of x prime, y prime. Is that true of these quantities Vx and Vy? Does Vx and Vy remain the same, only provided I specify that the point that it labels is the same point when I change coordinates? The answer is, for a vector that is not true, because if I have, say, a coordinate system like this and a vector like this be my vector. If I now rotate my coordinate system here and here, so I rotate it by an amount theta, then the two Vx and Vy that are used to represent this and this have now changed, because in the new coordinate system this is now a number like this and a number like this. So Vx and Vy have now become Vx prime and Vy prime. Okay. Because they refer to the same thing, a quantity whose direction and magnitude remains the same even as I change my coordinate system, Vx and Vy must be related to Vx prime and Vy prime. And it's this relationship between the components of the vector that defines how a vector transforms, that really defines a vector. Over here we said Txy is Tx prime y prime, But over here that's not the case. The Vx prime, Vy prime depend upon Vx and Vy, but they also depend upon the nature of the transformation that took you from one coordinate system to another. Okay? So let's just see how that would work. Here is one way of writing that relationship. I can write Vx prime and Vy prime is proportional to Vx and Vy, and the proportionality constant is the following. It's cos theta sin theta minus sin theta cos theta. So if I expand this, I have Vx prime is cos theta Vx plus sin theta Vy, and Vy prime is minus sin theta Vx plus cos theta Vy. Okay? So this is how I transform between two coordinate systems. And now you can see that this relationship between the components of Vx of the vector V, of the same vector in one coordinate system, are related precisely to the components in another coordinate system.
So this is only for the magnitude, right?
No, it's not the magnitude, it's all components. Okay? So every component changes when I transform my coordinate system. We can now ask what happens to the magnitude. So the magnitude of the vector V is Vx squared plus Vy squared square root. Okay, so this is modulus of the vector V. Okay, or somewhat more easily, for this particular example, let us look at the modulus of the vector V prime, which is this new vector here. So for that modulus, I have to look at the square of these components. I have to look at cos theta Vx plus sin theta Vy, the whole square, that's the x component squared. So this is, question is this Vx prime squared plus Vy prime squared? And what we are doing is calculating Vy, the modulus of the vector in the primed coordinate system. So here we can take this and write this as minus sin theta Vx plus cos theta Vy, square it, and now just try this out. Just work out what it gives. So you have cos squared theta Vx squared plus sin squared theta Vy squared plus 2 cos theta sin theta Vx Vy. That term is the same term but with a negative sign, that cross term in this particular case. But now you have sin squared theta plus cos squared theta times Vx squared plus sin squared theta plus cos squared theta times Vy squared. So this object is the same as Vx squared plus Vy squared, which is mod of V squared. Okay. So the modulus remains the same, but more than that, the direction of this vector, because I have taken care to make sure that my coordinates, that my components in the different coordinate systems have also changed. Because of that, the definition of a vector is a quantity that has a magnitude and a fixed direction, independent of whatever coordinate system I use, that remains the same. But in order to accomplish that, I have to write my components in those individual coordinate systems. I have to make sure they transform correctly as I move from coordinate system to coordinate system. Okay. From vector-like quantities, I can make other things. For example, suppose I have a vector called V and a vector called W. These are two vectors, which means I specify V by saying I have V of x and Vy, and I specify W by saying I have Wx and Wy. Okay, so now I have two vectors here, one V, one W, and I want to ask what can I do with these two different vectors? Can I make other vectors out of them? Can I make scalars out of them? Well, the answer is yes. The first is there is a scalar product of these quantities, by which I take a vector V, take a vector W, and write a dot in between. So this is the dot product of V and W, and this is a quantity which is Vx Wx plus Vy Wy. Okay. So now here there are no components but no vectors, no unit vectors. So this object looks like a scalar. Now the question is it actually a scalar? Well, that we can test because we know how these quantities behave when you rotate a coordinate system. You know that V becomes V prime, Vx becomes Vx prime, Vy becomes Vy prime, etc. Wx becomes Wx prime. So you can check that this is just Vx prime, Wx prime plus Vy prime, Wy prime. So the dot product of these two quantities remain the same in the two coordinate systems, the unrotated and the rotated coordinate system. Therefore, this behaves like a scalar quantity. So the dot product is one way of defining a scalar, but with these two, there are no other ways of defining a scalar here that takes in two vectors and defines a scalar quantity. But you can take two of these quantities and make a vector through something called a cross product. So if you have V and W, there's a somewhat interesting way of making a cross product by using, that is, make a vector out of this. And that vector is a vector called V cross W. In order to understand what V cross W is, we have to define what is the cross product of individual vectors here. So E1 cross E1 is 0. In general, Ek cross Ek is always 0. If I have the same type E1 dot cross E1 or E2 cross E2, E3 cross E3. But E1 cross E2 is E3. E2 cross E3 is E1, and E3 cross E1 is E2. Here are some definitions of what happens to these unit vectors when you take the cross product of them. Okay? Everything else is 0. Okay? So this is saying, if you look at how these indices appear, it appears as 1, 2, 3, 2, 3, 1, 3, 1, 2. This appears in cyclic permutations. So any cyclic permutation that is involved here leads 1, it gives you 1 on the right hand side, but anything else gives you 0. Okay? So now we can take, for example, what is V cross W, and V is just Vx times Ex hat plus Vy times Ey hat, and I want to cross it with Wx times Ex hat plus Wy times Ey hat. Okay? Now these are scalars, these are vectors, and the cross product really is concerned with the vector here. So if I expand this out, this looks like Vx Wx Ex hat cross Ex hat, then looks like Vx Wy Ex hat cross Ey hat, and there are a whole bunch of terms here. Typically there are 2 terms here and 2 terms here, so 4 terms altogether. This cross this, this cross this, this cross this, this cross this. And we can now work them out, because now we have done the first one. We have done Vx Ex Wx Ex Vx Ex Wy Ey. Now we have to add to this Vy hat Ey hat cross Wx Ex hat, and the last one is Vy hat Ey hat cross Wy Ey hat. Now this goes away and this goes away, okay, because automatically these are the same, Ek cross Ek. Those will vanish. The only one that survive is Vy, Vx Wy and Vy Wx. And to multiply that, we have to figure out what is Ex cross Ey and Ey cross Ex. And you can see that from here, what you will get is Vx Wy minus Vy Wx times Ez hat. Because Ez hat is the result that you get when you take Ex cross Ey. And the minus sign comes because here it's the other way around. Sorry, but here I forgot to, sorry, I said something wrong. If with any non-cyclic permutation, I don't get 0, I get a minus sign. I'm sorry, I missed that. Which is why this minus sign appears here. Gosh, terrible mistake.
So that is the 0 vector, right?
Which one?
E1
E1 cross E1, I guess that's true. Sort of logically with the definition, it should be the 0 vector. But it doesn't really matter to anything, whether I use that or not. All right. So the way to do this in more complicated situations is to suppose I have a full 3-dimensional vector V and a full 3-dimensional vector W. What I have is I can write V cross W as Ex hat, Ey hat, Ez hat, and then write Vx, Vy, Vz, and Wx, Wy, Wz here, and compute what is called the determinant of this. So this is written as Ex hat times Vy Wz minus Vz Wy minus Ey hat times Vx Wz minus Vz Wx plus Ez hat times Vx Wy minus Vy Wx. Okay. This is one way of actually computing what this is in a straightforward way. So now what we have done very quickly is to say that given two vectors, I can make a scalar product out of them, that a vector A dot B or V dot W gives me a scalar, but I can also make a vector out of it. And since I have explicitly written this in vectorial form in these combinations, you should check that this transforms like a vector. Remember that this, suppose I have a vector Z, I define this quantity Z as V cross W. I have to check that Z is also a vector in the sense that it transforms correctly when I change my coordinate system. So remember that when I change my coordinate system, V becomes V prime, W becomes W prime, but Z should also become Z prime, maintaining this relationship. So that's what vectors and tensors and scalars actually are. They're quantities that transform in particular ways when you change, whose components transform in particular ways when you change the coordinate system. Okay? A word about notation. When we wrote V dot W, the way we did this was that we said this is, first of all, write V as sum over I, Vi, Ei. Okay. Then take the dot product of this with a sum over J, Vj, Wj, Ej. This is the vector V, this is the vector W, this is the dot product between them. The dot product is not concerned about these terms because these are scalar terms. It's only worried about what happens to these two vectors Ei and Ej. So I can write this as sum over I and J, Vi, Wj, Ei hat dot Ej hat. Okay. This particular dot product is 0 if I and j are different and 1 if I and j are the same. So this becomes delta ij, and then I have a sum over I and j, Vi, Wj, delta ij. And the delta ij says that unless these two indices are the same, the answer is 0. So this just becomes sum over I, Vi, Wi, which is just the V dot W definition. So this is V1 W1 or Vx Wx plus Vy Wy as we wrote down earlier for the two-dimensional case. Just the thing about notation is that this is what's called Einstein's summation notation. Einstein recognized that these terms in which an index appears twice is always accompanied by a summation. So he said drop the summation completely and just automatically assume that whenever an index appears twice, it will be summed over. So we can take the point of view that Vi, Wi, whenever it appears, we will recognize it as Vx, Wx plus Vy, Wy plus Vz, Wz, etc., etc., etc. So this is called the Einstein. We mentioned this earlier. This is called the Einstein summation convention. Okay. Now we are beginning to get closer towards what we want to call a tensor. Again, a tensor is an object that's somewhat more complicated than either a vector or a scalar, but transforms in a particular way when you change the coordinate system. So one way of writing a tensor, so you can say tensor is like an ordered pair of coordinate directions and I will choose a little bit of a different notation here, more for consistency with that book than anything, that I have used V and W with a vector sign on top to denote vectors. But many books, and myself from at least for the rest of this class, might use the notation of V and W with a line underneath. This is a different notation for the same thing, it's just a vector. So we can define a tensor, for example, A, as the ordered product of two vectors. This is the simplest definition of a tensor, of the next higher order tensor from a simple vector. And tensorial quantities I will denote with two lines underneath. Okay. So it's the ordered product of two vectors, and I will tell you what that means. If V is V1, Vx, Ex hat, let's say, plus Vy, Ey hat, plus Vz, Ez hat, and the W is Wx, Ex hat, plus Wy, Ey hat, plus Wz, Ez hat. This expands out to Vx, Wx, Ex hat, Ex hat, plus Vy, Vx, Wy, Ex hat, Ey hat, plus Vx, Wz, Ex hat, Ez hat, plus Vy, Wx, Ey hat, Ex hat, and so on and so forth. You get the idea. There are 9 numbers now. And in these, this is what I meant by an ordered pair of coordinate directions, Ex hat, Ey hat, Ez hat, etc., 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 etc. There are 9 such numbers, and those numbers look like Vx, Wx, Vy, Wy, and so on and so forth. Okay. So in general, a tensor A is A11 Ex hat, plus A12 Ex hat, Ey hat, plus A13 Ex hat, Ez hat, plus A21 Ex hat, Ey hat, and so on and so forth. Ey hat, Ex hat, and so on and so forth. So it's a way of thinking about an ordered set of numbers with the interpretation in this particular case that they come from combining two vectors together. Okay?
How do we visualize a tensor?
You don't visualize the tensor because it's sort of harder to do. And we've already in some cases we've described tensors in terms of relationship between vectors. We said, remember, that the force exerted on this little surface element of some volume that sits here, the ith component of that force is given by a quantity called sigma ij nj times the little area element ds. And we said this, if I have a little surface element and n hat is a vector that is pointing out of that, the relationship between the components of that normal vector and the components of the force is mediated through a quantity here, which I called a stress tensor. Okay? So you can see that these tensors help to connect vectors, are related to vectors in some form, and they must transform in a very specific way. The reason is that suppose, again, this is a vector, this is a vector. So if I change my coordinate system, the components of this change and the components of this change. But both of these, because they're just magnitudes and directions, the transformation here and the transformation here must continue to connect these two quantities in the new coordinate system. So therefore that must be mediated by the sigma that sits here. So sigma must also transform in a particular way when you go between coordinate system and coordinate systems. Yeah, essentially. So there are, you have to, the new stress tensor in the new coordinate system will involve a product of two matrices that change coordinates that help you go from one coordinate system to another.
So in this case, the tensor can also be represented as the matrices of...
It can also be represented as a matrix in this particular case.
A11, A12.
Yes, exactly. So if you're in this particular case, I can think of this as a matrix A11, A12, A13, A21, where the first index indices is a row and the second index indices is a column. But when you go to more complicated tensors, for example, 4-component tensors, 3-component tensors, it's harder to think about it geometrically or even in terms of a, I mean, you can still write it down in terms of a complicated, say, matrix in higher dimensions, but it doesn't have a simple two-dimensional matrix interpretation anymore.
So here, the A with double underscore, what is that actually?
That is a tensor. So the notation that I will use for a tensor, in this case a tensor of second order, because it has two indices, one coming from each of these.
But that is not same as this matrix, right?
It is, no? It's exactly the same as these matrix, because this is just writing out the components that we obtain from here. This is just writing out these components here.
Okay.
It's exactly the same. Okay. Now, this definition in fact automatically shows you why these quantities transform between coordinate systems, because they are products of these basis vectors. As I go, I can always write this particular product. Remember, this Ex hat becomes Ey hat, some combination of Ey hat, Ez hat, and Ex of the primed quantities when I change my coordinate system. So I can always write this in terms of that, and then these quantities transform in a particular way that involves a direction cosines of the angle between these two things.
So they transform like a vector?
No, they don't transform like a vector. A vector transforms very simply, transforms with just one factor of that cos theta terms. So these will need other factors, more factors for more general tensors. You will transform with two factors in this case.
So what sort of multiplication is that actually, Ex times Ex?
So this is just a reminder of the fact that this is somewhat more complicated than a simple. So now I have a quantity that is two unit vectors together, and my tensor is defined in terms of this basic unit.
That's not a multiplication.
It's not a multiplication. It's just a reminder of the fact that there are two unit vectors together, stuck together like that. And this quantity A is defined in terms of this expansion. Okay. So once I write my A in this form or in this form, I know how A transforms because I know how these quantities transform. Okay. So this is an object that is higher than a regular vector object, because the regular vector would just have Ex hat, Ey hat, Ez hat. But now these have these ordered combinations, Ex, Ex, Ey, Ey, and Ex hat, Ey hat is not the same as Ey hat, Ex hat. They are different quantities, which is why there are 9 independent components of this tensor. However, when I change coordinate system, these components map in precise ways using from linear combination of the old ones into the new ones, just as the components of the vector did. Okay. Okay, some tensor algebra. There are analogues of what is called the tensor dot product, this definition, and the tensor dot product between two vectors that are, say, AB and CD. So I have A, B written as a tensor now, dotted with C and D. So this is some tensor here and some tensor here, and I have to define what I mean by that dot product. So that product is just A, vector sitting here, B dot C, where these are now the regular dot product, times D. Okay. So the regular dot product is Bx Cx plus By By Cy plus Bz Cz. So now this quantity has become a scalar. But this, so I can pull it a scalar, I can always pull to this side. This is really the same as B dot C times A and D, where this object is now a tensor object. I have taken thus two tensor objects, use the dot product to make one tensor object with a certain quantity that multiplies it. Okay. You can take the dot product of a scalar with a tensor. For example, we can take the dot product of a V with some tensor, let me call that A, put the line underneath. And this I can write as Vx Ex hat plus Vy Ey hat plus Vz Ez hat, and this is dotted with A11 Ex hat plus A12 Ex hat Ey hat, etc., 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 etc. So 9 numbers here and 3 numbers there. The rule is that this combines with the first hat here. Okay, so writing out the first term where this multiplies this and this. This is Vx Ex hat Ex dot Ex hat times Ex hat. Okay, that's this term here. Now this multiplied by this times A11. This multiplied by this is Vx A12 Ex hat dot Ex hat times Ey hat, and so on and so forth. But these here are just numbers again. So the Ex hat dot Ex hat is 1, Ex hat dot Ex hat dot Ex hat is again 1. So this now is a vector because it's some set of numbers multiplying unit vectors, Ex hat, Ey hat. So it's just some number 1 times Ex hat plus some number 2 times Ey hat plus some number 3 times Ez hat, which is a vector.
But we are not defining Ex dot Kx equal to 1, right?
So now the definition is that when we write it, take the dot product here, that dot product acts on the first of these elements here. That's the definition. And now what you should do is to check that this quantity, final quantity here, transforms like a vector. The aim is to construct these products, these dot products, these tensor products, dot products, etc., in such a way that the quantities that you get at the end transform correctly. That's the only way that you know that you're doing your job right. So we want to define this V dot A, a vector dot the tensor, in such a way that the resulting quantity here transforms like a vector. If you use this, that Ex hat sits and talks to the first element in this.
But the Ey of the vector is different from Ey cap of the
No, it's not. It's all written in the same coordinate system. The same coordinate system with ex hat, ey hat, ez hat has some tensor written in a11 ex hat, ex hat, a12 ex hat, ey hat. It's the same ex hat, ey hat and ez hat. I'm not mixing coordinate systems up. In one coordinate system, I ask what is the result of taking a vector v and letting it interact with the tensor A through a dot product. If I define the dot product such that this interacts with the first element of these two paired unit vectors, the quantity that I get at the end transforms like a vector. Okay?
So the end is a vector.
The end is a vector. The other somewhat nice way of saying it is that if I Vi Aij is the new vector, the components of the new vector Wj are given by Vi Aij, where I still use the Einstein summation convention to sum over the first index. And you can also check that writing it out as a matrix also satisfies this.
In the tensor dot product,
Hmm.
is the b dot c a scalar?
Where?
Here, dot product.
Here this is a scalar because it's two vectors combined together. And this really is the same logic behind that.
It is a tensor.
It is now a scalar because there is now a dot product here. Once I take the dot product, this becomes a number. It's just a simple number. The simple number I can pull out. No, it doesn't say the simple number has to be here. Just can multiply everything from the left. When I pull it out, I have b dot c, but then I have a vector here and a vector here. And these particular combinations I have defined as my tensors. An ordered pair of these vectors together.
Okay.
Hmm? Okay, let me just stop here.